Okay, now looking at our electron configuration and kind of bringing it back to our periodic table, yes, we use the periodic table a lot to find out our electron configuration, to do all those things with electron configuration. But the one thing that we should see is that our similarities in the chemical properties arise from similarities in electron configuration. So if we look at fluorine, look at the halogens, we see we have fluorine, we have chlorine, we have bromine. And when we're looking at these guys, we see that in fluorine's electron configuration, the last part of it is 2s2, 2p5. And then we see neon, or we see chlorine right below it, we see that we have 3s2, 3p5. Again, a 2 and a 5. Different energy level, but we see the 2 and the 5. And then we see with bromine, we have 4s2, 4p5. And so in that energy level, again, the outermost energy level, their valence electrons, they have the same electron configuration. So that's what gives them the same types of properties. And basically, remember, all of chemical bonding, everything is trying to become stable. Everything is shooting for that octet. It's shooting to have 8 electrons, 8 valence electrons, or 8 electrons which arise from the s and the p orbitals. They have to be full. 2 in the s, 6 in the p gives us a total of 8, and everything's good. So when we're looking at this, basically the way you can think of it, if you look at our periodic table, everything is trying to become a noble gas. Okay? And they're trying to do that the easiest way possible. So if you look at it, okay, our alkaline metals, okay, that's any orbital s1. So if you're looking at it, we'll say that dealing with anything like our sodium, it's 1s2, 2s2, 2p6, and then it's 3s1. Okay, all of the alkaline metals will end with that S1. So 3s1, 4s1, 5s1, 6s1, 7s1, they all end with S1. So if you look at it, what's easier for an alkaline metal? Is it easier for that alkaline metal to somehow gain 7 more electrons, or is it easier just to lose it? And they lose that 1 electron, and if you look at it, if they lose 1 electron, that electron configuration, 1s2, 2s2, 2p6, that's the electron configuration for neon. So for something like sodium, it loses 1 electron, and then it has the same electron structure as a noble gas. Okay, now because it can lose 1 electron and become like a noble gas, it makes the alkaline metals highly reactive with anything that will take the electron. It wants to lose that electron so bad that it's really highly reactive. Now when we look at the alkaline earth metals, anything that it ends with, it's going to end with number S2. So we use sodium, which was 1s2, 2s2, 2p6, and it was 3s1. Well, right next to it, magnesium, which is our alkaline earth metal, is just 3s2. And basically what it does is it loses 2 electrons, okay? And when it does that, it looks like a noble gas, okay? It has 8 valence electrons now, and it's happy. Okay, this makes the alkaline earth metals react with most anything. And the alkaline earth metals are a little more stable than the alkaline metals, so they're not as highly reactive. But the best way it can look like a noble gas is lose 2 electrons. Now, we're looking at our oxygen family. So we're looking at our oxygen family, we see, we'll just take oxygen for instance, which is 1s2, 2s2, and then 2p1, 2, 3, 4. Okay, the fastest way that it can look like a noble gas is to go ahead and steal 2 electrons or gain 2 electrons, because if it gains 2 electrons, this will go from 2p4 to 2p6, which again looks like a noble gas. Okay, they're going to be reactive, very reactive, and so we're going to see oxygen react with a lot of things because it's so close to being stable. Okay, the halogens are even more. They only need 1 valence electron. They only need 1 more electron to become like a noble gas, so they're going to be extremely reactive, and they're only going to have to gain 1, because we look 1 more over at fluorine, needs 1 more, and it looks like neon, which is a noble gas. And remember, all of this is about stability. So in our example, it says pure sodium is mixed with pure nitrogen. There are no other materials present, write the most likely ionic notation for each substance after they are allowed to mix. So when we're looking at sodium, and we've used that a lot, we know that sodium is going to be our alkaline metals. So we'll have sodium. It's more than likely going to give up the one electron it needs and become positive. Now nitrogen, on the other hand, if we look at nitrogen, and we can look on the periodic table. Okay, look at our periodic table. Our nitrogen is going to be right there. Okay, now what's nitrogen more likely going to do? We look at its electron configuration. It's 1s1, 2, 2s1, 2, and then 2p1, 2, 3. Okay, now what is it closer to? Is it closer to helium, or is it closer to neon? Well, neon's only 1, 2, 3 away. So what's it more likely to do? Is it more likely to lose 5 and become like helium, or gain 3? Well, the easier to gain 3. So when we're looking at our example, it gains 3 electrons, so it becomes more negative by 3, so it's minus 3. That's what's more likely to be, because it's easier for it to gain 3 than it is to lose 5. Okay, last example, it says describe chemical and physical properties of this right here. So basically we have neon and then 3s2. So let's look at our periodic table. Again, we always use this. We have neon, which is right here, and then we go 3s12, which is magnesium. Okay, so our magnesium is going to be alkaline earth metal. So we can say, talking about its chemical properties, it's more likely going to give up those 2 to become like its noble gas, neon. That's what it would do to become stable. React with something like a halogen or oxygen, depending on what's there, whatever will take those electrons.